So today we're going over the fundamental theorem of calculus and the trapezoidal rule. And the reason I have this lesson is because I found some other questions for you to kind of practice and work on. And this in particular is an example because I thought it was a little bit different than what we've seen. Now with this information that you are copying down, there is a graph of f, so I'm going to do my best to draw it out for you. Okay, so this is the sketch of f, and I'm going to put in a nice smooth curve connecting these points. Hopefully I do a good job. Okay, not too bad. Okay, so that's a closed circle, by the way. And you can see what points they're referencing to. So this is f. So when it says the graph of f is shown, this is what you should have in your notes. Okay, so we're going to go through A, B, C, D. And so at least there's no E, F, G, H, or whatever there was in previous lesson that we had. So here we go. If you don't have time to copy something down, please make sure you stop the video and make sure this is in your notes. All right, so A, to find the domain of H. Okay, so remember to pause the video if you need to copy anything down. So let's start with A. A says to find the domain of H. So if you look at H, it's the integral of f of t dt, okay, with respect to t, from 1 to 2x plus 1. Now, it's starting at 1, so if we look at the graph of f, if we're starting to shade in from 1 to some value, we would say it's from 1 to 10. Evaluating that integral, it can be 0, meaning that this is 1, or it can be up to 10. We can stop it at 5, okay, and we can evaluate the integral from 1 to 5. We can even stop it at 7, okay, or we can go all the way up to 10. So the x values that we have for our domain of H has to be something where this is going to be from 1 to 10. So since the domain of f is from 1 to 10 inclusively, then 2x plus 1 should equal 1 to 10, okay? So when we solve this compound inequality, we get this expression. So we can say that the domain of H, it's a capital H, so I'm going to try to be consistent, is from 0 to 4.5 inclusively. So those are the values that we can plug in, okay, to our upper limit of integration in order to evaluate what H is. Okay, so those are the only x values we can use based on what we have for our graph. So we're up to the next part. Remember to pause the video if you need to. So for our next part, part B, is asking to find h prime of x. So if I'm taking the derivative on the left side, I'm doing it on the right side. And use it to compute h prime of 3. So one thing at a time. So this is FTC part 1. Now if you remember, we need our u substitution in order to do this, okay? So h prime of x is going to be d over du, the integral from 1 to u of f of t dt, where u is going to be the 2x plus 1. Du is 2. You can also write a dx there, but I'm just going to leave it as 2. Remember, you're multiplying what we get by du. So what do we get? We're going to get that h prime of x is f of u du. So it's going to be f of the 2x plus 1 times 2. So we're going to write this I'm going to grab a different color. H prime of x, I lost my prime up there, it was just a dot, is 2 times the f of 2x plus 1. This is important because we're going to use this to answer h prime of 3. Okay, hopefully I didn't lose you yet. So now, by using our U substitution for FTC part 1, we got h prime of x, so now we need to find h prime of 3. And I ran out of space, so I'm going to erase this. And we get h prime of 3 to be 2 times f of 2 times 3 plus 1. So that's actually saying f of 7, okay? F of 7 is 4, so 2 times 4 is 8. Okay, so that's our final answer for part B. We're up to part C. Okay, so if you need to stop or pause the video to make sure you get your notes down, please do. In part C, it says, at what value of x is h prime of x equal to 0? So we need h prime of x to equal 0. We just found h prime of x to be 2 times f of 2x plus 1. So if I set that equal to 0, and I go to solve, I can divide both sides by my constant 2, and I'm looking to see where f of some value is going to be 0. So let's see what that might be. If we look at our graph, the only place where our answer is 0 is when x or t or u is 5. So what we're going to do, okay, if you look at this, we're going to set 2x plus 1 equal to 5. And we solve. Well, I don't need that step. You should see x would be 2. So that's our answer. What value of x would h prime of x equal 0? It's when x would equal 2. Okay, so once again, if you didn't get something from part C, make sure you stop the video, write it down in your notes, and we're up to D. At what value of x is h of x at its maximum? Justify. Okay, so the question is about the maximum. We need to find the x value of the absolute max, okay, of h of x. So sometimes our relative maxes are our absolute max, but just to emphasize, we're looking at our absolute max. So now we need the x value, okay, for h. If you remember your domain that we wrote for h, okay, that's your x values. It was from 0 to 4.5, okay? So what we're going to do is look at where h prime of x is equal to 0, okay? So, hold on. I'm going to need to erase some of this. Hopefully you understood all my little notes here and got it down. And maybe I'll even rewrite the domain. Okay. The reason why I want to look where h prime of x is equal to 0, if you remember when we do EVT and the procedure there, okay, f is a continuous function on the closed interval. Okay, we can see that. So if you want, you can say that. And it has a derivative. We actually found the derivative of h prime of x. And we're going to set our derivative equal to 0 to find any critical points, because that relative max or relative min or relative extrema that we may find may actually be the absolute max or min. So we did actually solve this before in part C. This gave us that x was 2. We're not only going to check that, but remember EVT, we're going to check these values also into our function. So if we check this into our function, okay, by the way, f prime is defined because, well, we've been finding it. We're going to figure out what h of 0 is, h of 2 is, and h of 4.5 is. Okay? So that's our critical point. These are our endpoints because any one of those can be a possible absolute max. So here we go. If we were to use 0, that means we're plugging in 0 into our function, okay, wherever we see x, and our function is defined by an integral. So it's the integral of f of t with respect to t from 1 to 1. So hopefully remember, when your lower limit of integration and upper limit of integration is the same, your answer is 0. Next one. So h of 2, if I plug in 2 here, I'm looking at from 1 to 5, okay? Now 1 to 5, if I shade in the area under the curve here, my answer is going to be negative, so it's less than 0. So far, it looks like x equal to 0 is going to give me my absolute max because it has the higher y value. Now let's just double check the last one. So I'm just indicating that that's negative, or we can say less than 0. So let's do 4.5. So if I plug in 4.5 here, okay, so we're getting from 1 to 10. So now looking at my shaded values here from 1 to 10, there's much more above the x-axis than below. So that means when I finish writing this out, I'm going to say that it is greater than 0. So you know what? Greater than 0 is much bigger than 0. So after doing all these little parts, we know now that h has an absolute max at x equals 4.5. And I think I ran out of space to write it. So I'm going to erase a little bit of this to write this out. Okay, so therefore, h of x has an absolute max at x equals 4.5. And our justification was the process of doing all of those steps. Okay? And that's it. We're good to go. So good luck.